My name is Anyin. I'm a professor of geology in the Department of Earth and Planetary Sciences at UCLA. My main research interests are tectonics of continents, and I study how mountains form, how plateaus form. But I also expand my research horizons to other rocky planets. I'm particularly interested in Mars because it has so many similar features to the Earth. And I'm also interested in other rocky planets such as Mercury and Venus. And we have this fantastic setup, and we're trying to do mechanical simulation to create structures, topography that we see on Earth and also on other rocky planets in the solar system. In the last 2 or 3 decades of space exploration, scientists have gathered so much data. And nowadays, all the data are in digital form. So you can download the data from computer free, and also there are all kinds of online softwares to help you to process the data. So the data are just at your fingertip. You can manipulate the data the way you want. So my research is really to utilize this, to take advantage of this amazing feature of space exploration to use the field observations taken from satellite images, analyze them, and compare them to Earth analogs. And then we use numerical models, and we also use analog models, as you're going to see today, to simulate some of the fault patterns that are common on all the rocky planets. And we try to explore the unified theme, a unified physics and dynamics to control the formation of those fractures. We can start with some of the maps. So this is a digital topographic maps of Mars. It's a battle-scarred. You can see many marks on it. So you can see there are sort of prominent topography on Mars. And if I fold this and just to see this area, so this is a very well-known area called the Tethys Rise. So it's very similar to Tibetan Plateau on Earth, but it's much bigger. So the size of this area is about 2/3 of North America continent. And the elevation of this area also much higher than Tibetan Plateau. Tibetan Plateau, the average elevation is about 5 kilometers, and this area is about 11 kilometers, so almost double the height. And those skinny, tall peaks, they're very tall volcanic constructs. This is a very famous one, the Olympus Mons, the tallest volcano on Earth. So if you look at this area, there's another feature which is also unique in the solar system. So this is a Valles Marineris canyon system on Mars, which is the longest and the deepest canyon system on Earth. We're interested in how this system formed, and also how this system relates to other fractures in this area called the Creatus Fossae. And even for someone who has no geological knowledge, you will find that there is some kind of geometric pattern that here there is a straight canyon system, and there are some kind of curved features here, and there are more linear features over here. So broadly speaking, there is kind of V-shaped feature. We call them a V-shaped conjugate faults. Those faults are also very common on Earth, as we're going to see on some other maps from Tibet. Okay, so here is another example of this type of V-shaped fault systems on Venus for this case. So this is the northern polar area of Venus. Again, it's a very, very large plateau, which is called Ishtar Terra, okay, which is similar to Tibetan Plateau. The northern and the eastern part of Ishtar Plateau, I highlight with the pen marks, also have those faults that have this kind of V-shaped geometry. This is also V-shaped geometry. So this is what we're really interested in, simulating what are the mechanical process to create those fractures. And in the next map, I'm going to show you similar features on Earth we're familiar with. particularly from an area I have spent a lot of time in Central Asia from Tibetan Plateau. Here is a digital topographic map. We play around with the ratios of a background elevation and elevations in this area. So you can see all the backgrounds like Indian plain and some large basins to the north. They're all put as a background, a gray color, to highlight this area. So this is Central Tibetan Plateau. And if you pay close attention to this map, you can see some of the features going like this. For example, this is one fault trace right there. And if you're careful, good observer, you can see there's another fault going like this. So fault like that, fault like that. Again, it's a V-shaped fault pattern. So that's something we really want to understand, why it is so common. And there's another one coming down. There's a smaller one over there coming down. And there might be another one over there, and another one over there. So, and of course, this is a very obvious one, big one coming down over here. So we're very interested in this kind of commonality of V-shaped faults we see on Mars, on Venus, and here on Earth. There are many places on Earth that display this kind of fault patterns. So we're going to move to the experimental work, and hopefully we can, if we're lucky, we'll create this pattern so you can see what kind of a process can create those faults. Okay, so in front of me is an experimental setup, which is used to simulate how faults formed in the rocky planets in the solar system. I'm going to direct you to my graduate student, Reith, who is going to give you some ideas about how the experimental apparatus was set up and what are sort of different boundary conditions that can be used to simulate different geological process.
Again, my name is Reith, and this machine here we have called Virtual Tibet, because it was originally made to model the India-Eurasia collision that he was just talking about, and the creation and the uplift of the Tibetan Plateau. So here we have multiple different boundary conditions. We have one main box that holds our analog material, which in this case we're using sand. And then we have 3 motors that can run gears where these different plates can move. So basically we have one boundary condition where this boundary can either move inwards, creating convergence, or it can move backwards, creating divergence. Same for this boundary right here. This can move backwards or forwards. And then one of my favorite ones, we can actually move this plate right here. And this is actually what we call basal shear. And it can move underneath this sandbox, creating flow below the surface where you see. So in a typical setup, we choose our material. So if you're doing just basically a friction model, you can use sand, because that's a great analog material for Earth's crust. You can also use viscous materials. So we kind of played around with silly putty sometimes. So in this case, we have sand, and the blue dots that you see on top, those are used as strain markers. So we actually have a computer program that when we take images of the model as it runs, it can pick out every single blue dot. And basically picking out each of those blue dots in a photograph, you can calculate or model the strain, or actually the velocity, which then you can turn into strain.
Okay, so now we're running the experiment. Robin just gave the command from her command center computer, so everything's automated. So we can set up a speed, duration of the experiment. So right now we hold this boundary and that boundary fixed. So make it very simple. Only move one, which we call the basal shear or basal plate. So which is driven by this step motor. It's moving underneath. Okay. So now you can see the surface of the sand start to deform. And if you look carefully, you can see the V's. See that? See those features? See those features we just talked about? So those are the features we are most interested in. So Mars, we see similar features like that. As I mentioned, Venus also have features like this, and many of them on Earth. So right now we're trying to play around with the scaling. So you can see that some of the V's are quite perfect, like this one, they really merge. Some actually don't get together, so there's still a spacing. So we're trying to play around with what is the width of the basal plate, which is adjustable underneath, and we can see how they deform with the time. We use the sand as analog models for Earth's crust because when we do experiment, the size of the experiment apparatus is much smaller than the real size of the world. So the parameter that we use is the Earth's crust thickness. So Earth's crust thickness is between 30 to 40 kilometers. Let's say 30 kilometers. And our sand here is about 3 centimeter thick. So the spatial relationship between these two, the ratio is a 10 to the 7th order of magnitude different between the two geometric parameters. So we have to scale the force by the same factor, 10 to the 7th power. So by doing so, the strength that hold the Earth crust together we call cohesive strength. So you have to reduce the cohesive strength by the same factor. So that means the material we use in the experimental apparatus over here has to be much softer using this factor to reduce. So when you do that, turns out that cohesiveless sand is the best analog materials for modeling Earth's crust. Okay, so we do all those experiments, we run it, we can simulate, not exactly, but approximately what we observe from the nature. The ultimate goal is to find the forces, what kind of forces, how the force is applied to deform the crust of the Earth, the crust of the Mars, and the crust of the Venus. Not only that, this experimental apparatus can go further. And you can see those yellow strips right here and a few others over there. So those are called the thermocouples. So we can actually put materials like a silly putty underneath, and those materials are temperature dependent, and they also depend on how fast they deform them. As we play with the silly putties, they can bounce as a ball, or you can stretch them like a viscous material. So we use this mechanical property to simulate deformation process, and by simulating the deformation that we can observe, we can also say something about the thermal conditions of the planet and how the thermal conditions are coupled with the mechanical process to deform the crust.